Good afternoon, scholars. Today we're going to be talking about the application of some of these ideas that we've discussed throughout our unit. Where we are currently in our geometry section is a place where we can apply many of the ideas that we've spoken about thus far this year and really turn them into, or begin to turn them into real life applications. Today I'm going to show you three different examples of how some of these methods have been used in the real world, and we're just going to play around with some numbers and see how to manipulate them. One thing to consider is once we start to apply these attributes or this methodology into real world occurrences, we're going to have multiple steps to our question. So I'm going to kind of show you three different examples and see how we can add some numerics or concepts to these. So let's take a look with our first question. So long down here in the bottom, we're going to label this section essentially circumference and area applied. And I just want to show you in this first example, one, how we can go about using area and density to help with population statistics, but then also to kind of work a little bit backwards, show how we can use numbers to misinform people as well. It's one of the powers of math is that you have, or as Mr. Friedel talked to you about in terms of rhetoric, is that if you have some appeal to authority, like numbers or some type of scientific calculation, you can actually use that to misinform people while still technically being accurate. Let's take a look at this first particular example. We're going to talk about population density in regards to an earthquake that happened in China in the year 2008. In the city of Sichuan, there was an earthquake, and as you may have seen in science class, basically there's shock waves that get generated from that portion of crust or where volcanic activity occurs. Then there's two series of waves that are sent outward, and that reverberate out, like essentially like a circle that expands. What we see here in our question is the farthest distance away that this measurement was seen, which is about 1,300 miles, which is give or take somewhere around, say, 800 miles or so. From here, we can see that this is like a radius, and since an earthquake wave, or your S&P waves expand equally outward, we can kind of describe this loosely as like, say, just a circle that's formed from a center location, such as the city. Our radius is going to be about 1,300 kilometers. And the extra information that we're being provided here is that in China, the most populous country in the world, there's an average for the entire country, an average of 137 people per square kilometer. So one giveaway here in this question is once we see information presented us as like squared, we're talking about something two-dimensional, like say area. In this question, we're being asked about how many people felt this earthquake. To apply our formulas from this week and most recently, what we're going to do is essentially look at our area formula. We're going to apply our radius to that to get the squared or kilometer squared measurement of that particular geographic location, and then we're going to figure out about how many people were impacted by this. So let's set up our equation first here. With area, kind of qualify this value or this formula as pi times r squared, or what we can say as pi times 1,300 squared. We end up getting a value of 5,309,291, and we're going to do 0.5 kilometers squared. So in this particular area, this is about the amount of surface area we would see if we're talking about two-dimension, not accounting for something, say, like mountains, which add distance and size for coverage. The next portion that we're going to look at here is if we want to apply this secondary factor, this secondary portion of our equation. We're told that there's a total of, or about, an average of 137 people per kilometer squared. So if we want to find out about how many people were impacted by this earthquake, we can then go ahead and say 137 people times our area, which gives us a value of about 372,947 people. When you're working with questions like this, one thing to consider is that you'll get decimal points as well. And we'll see this in our following question. But when you're asked how many people, you can't necessarily say a half person, so sometimes you might be given guidelines or there's like a logic to whether or not you apply that extra person. So with question, one thing to take in consideration, or one thing that's important to note, is that these are estimated values. And with estimated values, there's, in a sense, some type of misleading potential that exists. For instance, if we think about the population density of the United States, a country with obviously much smaller population number overall in comparison to China, the US only has about 36 people per square kilometer. Comparatively speaking to China, we have in the United States, we have slightly more land. We have more land mass, but a smaller population. So there's a couple things to consider there. In addition, since we're talking about a holistic approach to the population of the entire country, you can kind of misinform readers with information. Like, so take this for example. If we had an earthquake theoretically in Omaha, Nebraska, Omaha being the most populous, dense portion of the state of Nebraska, but if we're talking about 1,300 kilometers reverberating out from that location, the population density number is going to be kind of askew. It's not necessarily going to be helpful. It doesn't account for, like, say, the New York City metropolitan area, where there's almost 12 million Americans living in a considerably smaller geographic size than kind of like this, the whole entire state of Nebraska, where there's almost as many cows as there are people. So there's different metrics that you can use to, in a sense, have some type of authority approach. You know, your logos, pathos, ethos appeals that you learned about with rhetoric with Mr. Friedel, but you can use these numbers still to kind of misinform people. One of the favorite classes that I had in university, we had to teach a subject, and I chose to use numbers and politics and opinion polls to actually teach an entire lesson from a point of view that wasn't necessarily accurate. You can make a statement like, oh, 40% of people support a particular idea, and which sounds like a near majority. You can use different language. You can round up the number to 40 to be a near majority. And you can almost talk in a sense that's designed to misinform people with numbers. So let's take another example where we can apply circumference or our area. In this particular question here, we have a small entrepreneur who likes to design different pieces of jewelry. This individual states that they have, each necklace has about 20 centimeter diameter, as in if we were to draw a line across a circle necklace, and theoretically we're talking about in a circle form, that diameter is going to be about 20 centimeters long. In our question here, we're being asked how many necklaces can be made with 1,000 centimeters of wire. So if we have that amount of raw material, what can we do? How many actual necklaces can we end up making? For this particular question, if we wanted to apply our application, we're essentially looking for the length or our circumference. Our circumference formula we've talked about before is just our diameter times pi, and in this particular example, our diameter is going to be 20. If we find the length of one necklace, which comes out to about 62.831 centimeters, we can then go ahead and figure out how many go into 1,000. Our next step here would just be applying our total amount of material that we have, dividing it out as per necklace, and we end up getting a result of about 15.9 necklaces that we can make. So if you had a question here that says how many necklaces can you make or how many can be sold, your answer is not going to be 15.9 because someone's not going to want your 0.9 necklace. Your answer would be 15. So this is where we can start to see how we can apply what we've learned so far in geometry into like real world occurrences. But this is where we also have additional layers of questioning where you have to take the answer that you get and then apply an additional step of logic on top of it. Like we can't have, 0.5 people, we can't have 0.9 necklaces. We typically therefore have to round down essentially. Personal example from this, my father, when he would do his logistics for his delivery service, there's only so much content he can fit in his box truck to drive it to another store and things like that. His efficiency was based upon how many physical boxes that he can pack, and within that, how little extra space is left over. So that's like one thing that you can kind of begin to account for, where how many boxes can you get? Do you end up being able to benefit by having smaller boxes because you can cram them in different areas? Maybe your smaller boxes don't count for as much value as well too. And these are different things that as you go into like university or higher levels of math or business school that you try to figure out. And that's kind of what's called your systems of logistics, which is really fun class to study. The last example I want to show you is one that you're going to see often in terms of our like question types for homeworks, things like that. In terms of real world examples, what we're going to see here is like if you're doing any type of construction work and you have different objects fitting into the same places, like how much does one object remove from the space of something entire? Oftentimes with questions formatted in this way, you'll see it say like someone's making a garden and they have a box garden or a circular garden. They need to fill a certain amount of soil and such and such object takes away from that space. So what is our remainder? In this particular example, we're going to use only circles, and we're being asked to figure out what is the value of this shaded portion that we have here. I like this question a lot because you have to do a few different steps with it. A few jumps to conclusions you have to make just based on observation before you apply any formulas. The first thing that we have noted here is that we have a semicircle. And remember from our previous lesson, a semicircle is going to be half a circle. What we can get from here is that this outside figure, the radius is actually twice as long as the radius of this particular circle, or it's equivalent to say its diameter. If this distance here from our point, our center point, up to the top of the circle, our radius is 2 inches, that means the length down to the bottom is also 2 inches. If we were to then holistically look at our semicircle, the radius of the semicircle itself would be a value of 4 inches. So in this particular question, if we want to find the value of this shaded area, we first have to find the value of our inside circle figure. Next, the value of just the semicircle itself, and then subtract the two from one another. So our first step that we're going to do is find the area of the small circle. So our area of the small circle is going to be equivalent to r squared times pi, or 2 squared times pi, which we can just leave as 4 pi. Next, we want to find the shaded area, the value of the semicircle. In terms of an equation for this, what we're going to do is essentially find the value of the entire circle, and then we're going to apply our sectors concept and basically look at it as half of that whole value. So if we want to find the area of our large circle, we're going to do essentially the same thing. We're going to apply for our area formula, do 4 squared pi, which is equal to 16 pi. But then we're going to divide it by 2 because we have a semicircle or half a circle. And we're going to get a value of 8 pi. Lastly, if we want to find just the shaded area, we're going to go ahead and take our semicircle value of 8 pi. We're going to subtract the unshaded area of 4 pi, and we're left with 4 pi as our answer. So this is a nice real-world example that you'll see. I like questions like this because you have to do extra additional steps of logic, and then you have your real-world consequences associated with them. For today, this video is a little bit shorter. What you'll see is in your Google assignments for today, there's just a few questions being asked for you that relate to this particular unit. You'll see in that assignment that there's actually the independent practice for the following unit as well. I give you everything in one spot so you can just submit it in one spot as well within our Google assignment. Your exit ticket for today is only going to be questions related to this type of real-world application. We'll see in your second Edpuzzle video for today as we begin our next unit. Our next unit is just definitions, and I wanted to basically end this unit with just a short exit ticket, and all you'll have to do to complete that is go on to Jupyter. You have a few questions to answer that are very similar to your independent practice questions. My suggestion for you is before you start the second Edpuzzle video is basically just go ahead, do the independent practice questions, and then do your exit ticket, and then start your following Edpuzzle. So as always, if you have questions about anything, please hop into office hours. They're from 1:30 to 3:30. You can check it out on your Clever. You also have the number or the room number listed on Google Classroom as well too. It's in the feed. It's one of the first things that is there. All right, so if you have questions, let me know. Peace.